voltage rule. So again, we're flipping back and forth between voltage rule and current rule. I gain 20 volts here, come along, cruise along. I'm gonna go this path this time, so I'm gonna gain 20. I lose something here, I lose something there, and I'm back to 0. Well, I can now figure out how much my voltage loss here is because I know the current. I can figure out the voltage. Ohm's law, yet again. So my voltage difference, well, the magnitude of my voltage difference, is 5 times 2.4562. Which is 810.
Yeah.
Okay. Yeah, volts. So if my potential difference across that, we can see how long I can maintain this. So I've got I lose 20 volts there. I lose 12.2810 volts going in that direction. So if I know the potential drop here, I can figure out the potential drop across this. And how would I find it? Yep. So 7 point something. So my potential drop from here to here, delta V, .7190. So I can now find the current flowing across the 4 ohm. Because it doesn't matter which path I take, it's the same potential drop. So going across here, I got that drop, I got that resistance, I can find the current flowing across the 4 ohm. Using Ohm's law yet again. So that's going to be equal to 4I. I4, I guess. I guess 7.7190. So I4 is
1.929. Well, because there's 5 at the end.
9298. Okay. So that's the current flowing across here. So we now know I've got 1 point, just wrote it down, 9298 amperes flowing across there. I've got this junction here where I know I've got 2.4562 amps flowing out of it. I got 1.9298 amps flowing into it, so I can figure out now the current that's flowing down here. And how would I do that? Ooh, way complicated. Junction rule. If I know that I've got I had the number there, 2.4562 amps flowing that way and 1.9298 amps flowing that way, what is the current flowing down this way? Yeah. Whatever flows in equals what flows out, so the difference between these two has got to be what's flowing in here. So that minus that gets us
I got 2.526.
no, we can't do that.
You can't do that. You said subtract. subtract, right?
Yeah, this minus that.
Yeah, that's right.
You did 2.4562 minus 1.9298. Oh, 0 point, I misheard it, I apologize. So 0.5.
264.
Almost there. All right, so again, now we go to the voltage rule. I can take some path here. I'll know the voltage, so I gain 20 here. Actually, how much do I lose there? Let's simplify that. What's my voltage drop going across that resistor? Or how would you find it?
I did 20
You did 20 divided by
3.
3. No.
Yeah.
It's gotta be, define the voltage drop. It's current times resistance. So 1.5 something. 5.7.
1.5792.
Oh, and we did the voltage drop across the 4. That was the, going that way, minus 7.7190. All right, so now we just did a current rule to figure out the current there. We now use voltage again. So I gain 20 here. I'm gonna lose something across that or that, either one. I'm gonna lose 1.5792 volts there, lose 12.2810 volts there, and I'm back to 0. So how much do I lose here?
20 minus all those things.
Yep. So 20 minus that gets us, looks like, oh, we have a second calculator, possibly a third.
You see a giant one stuck on a board. Giant calculator.
Oh. I'm sure they exist.
Probably, it'd be kind of funny.
So what is it? Six point something.
6.1398.
All right.
Seems weird.
So I know the drop here, it's the same either way, they're in parallel. So, well, I can figure out the current flowing across this one. Because it's just the voltage divided by the resistance. And so my current flowing across here is going to be 6.1398 amperes. That's not right, something's off. All right, where did it all go awry?
What was it? It was 3.3 times 0.5264. Is that the last one we did?
Yeah,
Yeah, that's right. 1.5792. And this brings up an interesting point. If we're doing these problems ourselves, we miss one little mistake in there somewhere, and the whole problem's screwed up.
yep. Oh, just wait till we get to the more complex ones. So I'm guessing one of these fractions is wrong. So 2/3, so we started out with 1/1 plus 1/2. That's 3/2, so flip it 2/3. Okay. Then we add 3 and 2/3, so that's 11/3. Okay, good for that. And then we have the 11/3, 3/11 and plus 1/4 on denominator of 44. Oh, that's not 14.
Yeah. Well, 23.
23. So, which doesn't reduce, it's 23 is prime. Which then affects,
Everything.
yeah, pretty much. Okay. Hopefully you see the process. We're gonna, I do know that if we had done fewer than 4, well, again, any rounding error is gonna get propagated through, which some students will do the whole thing in fractions. I guess some calculators deal with fractions better than others. And I will tell you, as a grader, it's a lot of fun to try to figure out where the mistake is. The hour I would spend. Part of me wants foreclosure, wants to go back and redo it, part of me just doesn't.
Just so you can be like, hey, it's easy, all it equals 20 volts again.
Yeah, pretty much.
Complete the magic trick.
Or my classic, it worked before, I don't know what happened this time. All right, I'll leave it up to you. Go through and actually get the correct answers, or assume that you understand the process, which is the important thing, and move on.
Extra credit.
In here.
Find another way.
Move on?
I'm indifferent, whatever you.
Okay. Oh, either way. Anyone else with an opinion?
I say move on.
So we got 2 move on, indifferent, and another move on, Brian?
Okay.
Okay, all right. Okay. Let's go do something else, where a tiny mistake can really mess things up. And also, if we'd done it all correctly, you wouldn't have seen it as blatantly, but we also were able to see how we were able to go, oh, wait a second, there's something wrong here. So now, the multiple batteries. 3 volts, 5 volts, 7 volts, 2, 4, 8, 6, 7. We can't do the equivalent resistance for this. We have 2 resistors in parallel and series that we could do, but the battery really messes things up. So we can't go through the technique we just did. There are 2 primary techniques for solving the current flowing across each resistor. And I will tell you that the last question of the next test will be a problem very much like this. The numbers will be different, batteries might be flipped, but the basic look is this. I'm going to take you through 2 physics techniques, and then I'll go through 3 different math techniques, but there are more than 3 math techniques. The 2 physics techniques basically get you a set of equations which you then have to solve. So technique number 1, or method 1, I can't remember how I worded it in the videos, is one current per path. The other one is one current per loop. So if we think about the first technique, paths, I have a junction here and I have a junction here. I have three different paths to get from one to the other. So I'm going to create a variable for each one. Now, which way the current flows is irrelevant to picking this. You could, if you want to, sort of think through of what your guess is the direction of the current flow, but it is not required. So I'm going to ignore that. And I'm just going to go from bottom to top. So this path here, I'm going to call I1. This path here, I'm going to call I2. And the current flowing through this path, I'm going to call I3. Now, my gut tells me is that the I2 is in the wrong direction. And that's okay. What will happen is I'll get a negative value for I2, and that just means, oh, it's the other way. I don't have to redo it. Now, once I've identified one per path, I'm going to do one other thing here just to eliminate some of the writing I have to do. I'm going to let B equal I1, C equal I2, and D equal I3. I started out with I1, I2, I3, just to emphasize that these are currents, but I'm going to use B, C, and D, because the more subscripts I write, the more chance I have of making a mistake. I have three unknowns, I need three equations. The first equation is going to be the junction rule. You either take the top or the bottom, it doesn't matter. I have only two junctions in this particular problem. Current in equals current out. So I look at the top junction. I have three currents flowing in. So I1 plus I2, I was going to use B, C, and D. B plus C plus D equals the current flowing out, which is 0. The other two equations will come from the loops. I have three different basic loops here. I have my left loop, I have my right loop, and then I have the outer loop. They are not in three independent equations, and so I can't just use that solely. I have to use the junction in conjunction with it. But of the three choices for the loops, I need to pick two of them. So I got left, right, and outer. And it doesn't matter which two you pick. Anyone with an opinion? Okay. So I'm going to start here, because personally, for whatever childhood scar, I like the first thing to be positive numbers. I'm going to start here. I'm going to go in a clockwise direction, and I'm just going to do the right loop. So I'm going from the negative to positive side of my power supply. So I gain 3 volts. Cruising along, going across the 4 ohm resistor in the direction of the current that I said. And if I'm going with the current, I lose potential. So minus 4V. Coming down here, I'm going across the 6 ohm resistor opposite the direction of the current. So I'm going to gain plus 6C. I go across the power supply from the negative to the positive, plus 5. And then across the 2 in the direction of the current that I established, minus 2V equals 0.
Why did we have it equal 0?
Because the sum of the voltage gains and losses should add up to 0.
Gotcha.
I end up back where I started.
I'm going for 5, but didn't write like 5D.
The 5 was the power supply. That each of these are voltages. That's of the power supply. That's Ohm's law. That's the current times the resistance.
So we correlate the I with the ohms and not the power supply.
Right.
Yeah.
catch your drift on that. Yeah, this is I times R,
Yeah,
this is just the potential difference of a power supply.
yeah, that makes sense.
Okay. Now, some students will write units in here. I would not recommend writing units, unless I got something bizarre in there, and I haven't done that yet. If you put in units, you're just cluttering more letters. But that, you do you. Now, the left loop, oh, that was the left loop. The right loop, well, let's do the right loop. I'm gonna start here, and I'm gonna go counterclockwise. I could start anywhere, just as long as I end up back in that spot. And it doesn't matter if I go clockwise or counterclockwise. Again, I start just before battery. This is my personal choice. And then I go in the direction, so my first number is positive. Again, scars. So again here, I'm going this way. I don't have to go in the same direction as the current, it's just a coincidence that I am. So I start out with 7. Cruising along this 8 resistor, I'm going with the current that I created here, D. So minus 8D. Now cutting down the middle here, going against my current, so this is plus 6C. Going across my power supply here from negative to positive, plus 5 equals 0. If I had done the outer loop, this is not an independent equation, if I had started here and just done the whole thing, I would have had 3 minus 4B plus 8D minus 7 minus 2B equals 0. And if I took this equation and subtracted this equation from it, I would get this.
A little lost.
All right? Where?
So, we're starting at each power supply and working around?
Yes.
What about the middle power supply?
That was taken into, this was the